We're almost done with the quizzes grading, but we have 2 things want the makeup. So I'm going to hold the grade, and coming Tuesday, I'm going to give the quiz back. So you feel good, right? Pretty good? No? Okay. Okay, so today we are going to finish lecture 2, double sideband suppressed carrier. So last time we talked about transmitter part, right? How can we modulate our signal from message to carrier? Today we are going to talk about how can we demodulate it. And if we still have time, we talk about the most advanced member in this family will be single sideband. So last time we talked about double sideband suppressed carrier, just no carrier, right? And in your time domain signal, there will be a phase reversal. Yeah. And we mentioned my efficiency is 100%, right? All power used to transmit message. So we achieve the goal we want to beat, right? We increase our efficiency to 100%. However, in the transmitter side, still pretty simple, but at the receiver side, we have to use coherent demodulation or coherent detector. So this one is way more complicated compared with envelope, right? Detector. So let's look at the block diagram and go through each step. What's going on? So this is the block diagram at the receiver side. This is my modulating signal, right? Goes into my receiver. Step 1 is a mix with a signal. So look at this signal, right? This signal is V cosine omega CT. We have carrier, pure carrier mixed with the input. Then my signal will go through a low pass filter. After that, we get message. So let's take a look, right? What's going on at every step. Okay, the input signal, right? AC, the carrier amplitude, right? Message, carrier. Point B, my signal, we just mentioned, right? Pure carrier with a little different amplitude. Now, point 3, the multiplication of those two signals, we have A, right? B, xt cosine omega c cosine omega. So we have cosine omega c squared, right? So let me write one more step for you. A, C, B, right? We have xt. Cosine square omega ct. So we have A, C, B, xt. 1 half, right? Half. 1 plus cosine 2 omega ct. This is exactly the same as the equation over here. So now we have two parts, right? Two parts. One is DC component, right? So this part is only message. The other part will be message modulated. Another carrier. This carrier frequency is 2 omega ct. So we have a DC component, right? And even higher frequency component. Okay. So any problem? How can I get this one? Now this signal will pass low pass filter. So if I choose my low pass filter's cutoff frequency carefully, I can remove this part and keep this part. So we get message demodulated.
Remove what part?
Yeah. So we have a low frequency, right, and high frequency. So high frequency will be removed by this low pass filter. Actually, next, yeah, we will try it. So the output of the receiver, we have AC B over 2 XT. XT is the message. So like a constant scale, right? Time you input. So we demodulate our signal, we get our message from carrier. Okay, then we are going to talk about two important things in this structure, in this scheme. Okay, let me. Okay, so this one is receive signal, right? We receive it. This one is something we put into my receiver. So this signal is really important, really important. It's a sinusoid, right? It's a sinusoid signal. So B we can adjust omega C should be the same as omega C. And there's no phase, right? There's no phase. The phase also should be same. We want omega C and okay, we want this omega C is the same as input signals carrier. We also want no phase difference compared with receive signal and the local reference you use. So we talk about theta first, then we look at omega C. So in this slide we have if there is a phase shift, right, there's phase, if we do not have very good synchronization, if we have a phase difference from my local reference compared with my input, let's see what happened. Okay, so I'm going to write a little more details for you. Three, right? And so point one still the same. Point two change a little bit. 1, 2. If x2t is b cosine. Okay, I just copied. I want to show you why my x4t is no longer the same. There is a change. So This is my input, right? This is my input. This is my input. And B cosine omega ct plus theta is my not perfect reference. So this is my, we call it reference signal we use to mix with my input. So if I do not have perfect phase, if my phase, does not lock well with my input, something will happen here. A, C, B, X, T. Now cosine times cosine. So we have these two phase angles summation here, and the difference, right? And difference. Now my signal will go through a low pass filter, so high frequency part will be blocked, removed. We have AC, B, SP. Half, right? Half cosine theta. K X key. So my signal will be a scale, a constant time xt, but modified by cosine theta. If theta is no bigger. If theta close to 0, right, cosine 0 is close to 1, so pretty good. If theta close to pi over 2, like it's 0, so my output will be very, very small. If the phase difference bigger, my output will be smaller. So we really want theta as small as possible, right? If not 0, so we want our theta as small as possible. How can we achieve this one? We use phase lock loop. So in your lab, right, you're doing, or you will do phase lock loop, right, in the lab. Okay, any problem for this one? We really want no phase difference, or phase difference as small as possible.
And that happens because it's not at the same frequency?
Mm-hmm. No frequency. Yeah, so generally, right, if you know it's channel 1, channel 2, channel 3, you'll know the frequency, right? But phase, we really don't know even you know the initial phase from a transmitter, but when it transmits to a receiver, the phase is also changed. So we have no idea what is the phase. Only after we receive the signal, we can figure out what is the phase. Because it's transmitted, right, through the channel. So you are moving, right? Station may be there, but you may moving. So the phase is changing. It's changing. The receive signals phase is changing. So even you have a very good local oscillator, may still be some difference. Okay. Okay, this picture, we showed this picture last time. So just quickly talk about what happened at your receiver side. So this is my modulated signal and my input, right? We know the envelope no longer the same, but close. Here, after the mixer, right after the mixer, this is my envelope, and it has a low frequency. And inside is the high frequency, 2 times right higher compared with the input. So go through a low pass filter. The low frequency signal will pass, and the high frequency signal will be blocked. We get our signal demodulated in frequency domain, we can find that, remember we plot, right? So we have the modulated signal here. So this is modulated signal. When we go through the mixer, it may move here and here and here, right? Mixed with sinusoid. This part move here and over here. So blue and green combined, we have this part, double, right, superposition. This part, another part will be blocked by this low pass filter. So this will happen in time and in frequency. So we obtain the message. Okay, then we are going to talk about how can we get.
How do you know the right phase to lock onto? Because if you pick the wrong one, aren't you going to get the negative of the signal? Like cosine of...
Yeah, if it's
Zero.
pi, right? If
Yeah.
the phase angle is pi, yeah, you'll get negative.
So how do you tell which one is the right phase to lock onto?
Which one? So let's talk. Let's talk about the method we're getting the phase first.
Okay.
Okay. So there's two things we have to know, right, before we add the signal to my receiver, omega c and theta. So which one you will use? So in my slide, we talk about omega c first, then theta. So if we want to talk about theta, we can talk about theta first.
Okay, it's up to you.
Okay, so which is, let's. Okay, so we talk about omega c, right? How can we get omega c? We can have a local oscillator. However, people use even smarter. I believe it's even a smarter method. So we kind of extract reference signals frequency from received signal. So let's see what can we do. Received signal will mix with itself. Step one, then go through a bandpass filter. This bandpass filter is specifically designed, can only pass 2 times of FC only. Then we have a frequency divider. Divide the frequency by 2. And this signal will have exactly the same frequency as your input. So let's go through step by step what's going on. So let me use okay, let me use this one. Okay, bandpass filter. And frequency divider. Okay, I call this point A. This point B. Let's see what's going on. Okay, this procedure is not required. If you can follow me, it's good. If it's kind of hard, just remember the final result. So in order to make my calculation a little simpler, we use a special method. Okay, cosine omega m of t will make my calculation simpler. If you're interested, you can use a general signal. It will be way more complicated. So my input will be right a cosine omega m of t cosine omega c of t. This is my input, right? Input. My message, because I use a simplified sinusoid as a message. So any problem of this one for the input? Okay. Here, signal mix with itself. So at point B, point A, x A, will be A square, right? So I have square. So from this step, you can use multiplication first, then square, or square then multiplication. So it's up to you. Okay, I decide calculate the square first. So, any problem here? Now, I'm going to calculate, right? The cross term, right? And all the four terms. So I have four terms, right? Four terms. DC component 1, 2 times omega m of t, 2 times of omega c of t, and the cross term. Those two already is the simplest version. Only I want to do is kind of show what's going on here for the cross term. So. Okay, so here, if I look at an entire signal, it has DC component, right? 2 times of my signals frequency and 2 times of my carrier, and omega c plus omega m. Omega c minus omega m. So if you plot it over here, right? I'm going to have 2 omega c, right? Omega c minus 2 omega m. 2 omega m. This one is 2 omega c minus omega m. Okay, I have line, we have 1, 2, 3, 4. 4 line spectrum. This signal will pass a band pass filter. Which one can pass? Only this one can pass, right? Because my band pass filter is designed based on only pass 2 times of FC, so 2 times of omega c. So let me write. Okay, over here. Cosine 2 omega c of t. So I only have my target frequency pass, my filter. Okay, the only tricky part may be this one. So now go through the filter. I get a squared over 4 cosine 2 omega ct. Then frequency divider, right? Frequency divider. Divide my frequency by 2. That's 2 is the over 4 cosine omega CT. We divide frequency by 2. Okay, K, right? Cosine omega CT. So we call this method reference extraction. We extract reference from you receive signal, and it's way more accurate compared with you have local oscillator. We know the high resolution oscillator is really expensive. Okay. And any problem here about what we do, right? We extract the reference from received signal. So because my carrier frequency is embedded in the signal, so we can extract it. And this method also used in many other areas. For example, digital communication systems, right? You have to know the clock, right? You have to know how long is a bit, right? So find clock is very important. I still remember the first time I interviewed with Connection, he developed DSL model. So one question they asked me was, how can you find the clock of received signal? So I searched in my mind. Okay, I mentioned. Okay, I'm going to use cross correlation method. So that is in my mind, right? So you have digital sequence, right? Find the correlation. The highest correlation will give you the clock, and the right answer actually is extract the clock in the signal. Right, my method is okay, but not simple enough. So let me show you. Okay, I have 1001, so you can find, right? This is the clock, right? This is clock, this clock. Clock is embedded inside this digital sequence. So they don't have to use the correlation method. They can find the clock. Okay, however, if I transmit my information how about I transmit 1000 continuous ones or 100 continuous zeros? The clock is gone, right? There's no clock. There's no clock. So people also use another. They design some code. This is for 0. So people develop called Manchester code. For Manchester code, you have a high and a low for bit 1, low then high for bit 0. So in this case, right, no matter I have how many continuous 1 or 0, clock still built in. Each bit, every bit, you'll have a clock information. Right, so extract reference from your signal is very popular. Okay, any other questions, problems? Okay, now we talk about the problem from phase, right, from phase. So now we have perfect omega c. How about theta? we just went through this one. So we use phase lock loop, right? Phase lock loop. We still try to find a phase based on your input. So in this block diagram, similar, right, to our receiver, we have a mixer source, right, and we have a low-pass filter. The only difference, this time my input to the mixer, input and a controlled, right, a signal, a changing signal, right, a time varying signal. This signal generated by this voltage control oscillator. So your frequency can be changed, right, can be modified based on the input, So this signal is sinusoid. This one compared with this, or mixed with this one. So you can imagine we have the addition, right, and the subtraction part. Go through low pass filter, only the subtraction come back. So the difference will be used to control your VCO. Once those two signals are very, very close, we have pretty high gain. So we believe those two are very close. This one will be my output for my reference. So we use phase lock loop to lock the phase, to reduce the phase difference. So like you know, anybody has experience to tune a old TV set or radio, no digital tune, right? But you use your manual, right? Use your hand. So somebody will tell you, you have to listen, right? You listen, you turn to this side. It's good, right? I try to little bit more. Even if it's worse, I go back, right? I go back. So I remember 20 years ago, right? Maybe we are trying to kill the antenna, right? Somebody inside the home look at the TV set. Okay, go back. No. The other way, right? So we kill that. Something like this, right? So you find it's good, right? I go a bit further. If it's better, I go even further. If it's bad, I go back. So I can tune it. And once I believe performance is acceptable or good, okay, we're going to fix. So phase lock loop widely used in communication. Later in chapter 6, we talk about phase lock loop one more time. So any problem, any questions? I believe there will be a lab, right? Okay, I think so. So we talk about so in phase lock loop we have a signal multiplier, low pass filter, and a voltage control oscillator. In my block diagram, not very complicated. However, in order to find perfect cosine omega CT, we have frequency. We have a frequency reference extraction, right, for omega C, and we have phase lock loop for phase. So that makes our receiver side way more complicated. Okay.
So how does the phase lock loop actually find the right phase? You're saying it kind of tunes it until it finds the right spot. So is there a period when you're sending a known signal where you tune it to get what you want?
Actually, for the details in the circuits, I don't know much about that.
Okay.
Yeah.
So I'm just trying to understand how we know what phase, like, is it going up first and then down, or is it going down first and then up?
I really don't know the details there.
Okay.
Yeah, but from the block diagram we know the control signal we use will be the difference, right? So we know here after mix and low pass filter, the difference of XCFT and output of your VCO will be used to control this VCO.
Okay.
So we believe that when my input is very, very small, right, I can just stop, change my frequency.
Okay, it's like negative feedback.
Yes, negative feedback. And for VCO, general concept will be F, right? Is this right equation? I cannot remember. Or omega maybe, right? So you have LC, right? How LC circuits. L generally we don't change that, but if you change your C, the frequency will be changed with oscillator.
Okay.
Yeah, remember that in
Yeah.
your 210 class. So you usually have a tunable capacitor.
Okay.
So that is the general idea, but I believe in the circuit it's way more complicated. And I remember, there was a book talking about phase lock loop. Yeah, a textbook for that. Okay, so here is one more thing we talk about double sideband suppressed carrier before we move to single sideband. If we use a double sideband suppressed carrier, we can transmit twice the information over same bandwidth. Okay, so let's look at what can we do. We have two messages, two information signals. One mixed with cosine omega CT. The other branch mixed with sine omega, so they have orthogonal, right? So cosine and sine are orthogonal. Then we transmit them together. So in this way, we can transmit twice information on the same bandwidth. In communication, digital communication, we call it QPSK. QPSK. So we have this is transmitter side. So we have two double sideband suppressed carrier transmitter. Combine them together. So only difference, they have two different. They have same frequency, right? But 180 degree phase shift. Oh no, 90 degree phase shift, right? Cosine and sine pi over 2 phase shift. So this is transmitter side. And we have two channels, right? C and Q, so we call them IQ channels. After we talk about the details here, I give you some details about what is IQ channel and why we want to use it. So this is the transmitter side. Okay, receiver side. So at receiver side, they have two coherent detectors, two synchronized detectors. Okay, branch 1 mixed with cosine omega CT goes through low pass filter. Branch 2 mixed with sine omega CT goes through, actually, same low pass filter, and we get information 1 and 2 and 2. So let's quickly go through what's going on at transmitter, then at receiver. And if you have problems, you can always go back. So here will be, this is my so this is a signal from transmitter, right? From transmitter. Message 1 mixed with cosine. Message number 2 mixed with sine. Right, straightforward from the block diagram. We get phi t equal f1t cosine omega ct, f2t equal sine omega ct. Okay, now here I have the receivers, right? Branch 1 and 2. So pass 1, pass 2. Pass 1. So phi t mixed with cosine omega ct, right? We just copy everything. So F1t cosine omega ct times cosine omega c, we have cosine square. Second round we have sine, cosine, and we did many times, right? Previously we did many times. Cosine square we get half plus cosine 2 omega ct. So this part from ft cosine square. And sine, cosine, if you check the table, we get sine 2 omega ct. So this is pass number 1. Any problem I can get 1, 2, 3 parts. We notice that, right? This is message. This is high frequency part, right? This is high frequency part 2. Okay, so this is the second branch, second pass. Similar, right? Similar, not equivalent, but similar. So we have 2 omega ct, 1 minus, right, cosine omega 2 omega ct. Now, signal here and there will pass low pass filter. Definitely, right? This one will be cancelled, right? This one will be blocked. Here, this one will be blocked. And sine 2 omega c cannot pass my low pass filter. Only here and here will go through my entire receiver. So after low pass filter, the output of pass number 1 will be half your input signal number 1. E2t equal half F2t. So we call this QPSK or QPSK. So this is what people really do in the transmitter and the receiver side. Okay, here something any problems, any questions? Since we talk about QUAM, QPSK, and also in the picture, right, we have Q, right, we have IQ, we have IQ channel. So I want to talk about a little bit IQ channel, why I want to use it, what is the benefit of using IQ channel. Not required, just, kind of give you some contemporary, right, or modern technique we use right now. So IQ. So we have in phase. I means in phase. Q means quadrature. So we have two channels. Why want to use it? So we talk about ASK, right? FSK, PSK. So we change amplitude, we change phase, we change frequency. Change amplitude actually is pretty simple, right? However, change a carrier's phase is not so simple. If you have 4 PSK, 8 PSK, or 16 PSK, or even more, that means you have to change your phase totally from 0 to 2 pi. You have 4 choices, 18 choices. And QUAM, right? QUAM will change both amplitude and phase. So how can we change my phase in order to transmit digital signal? We use IQ channel. find a sinusoid signal, right? This is my amplitude, right? Frequency and phase. So how can I use IQ to deal with phi, deal with this phase? Okay, here actually I just switch position phi and omega t. Okay, next step, please pay attention here. Okay, please pay attention here. Now, sine alpha plus beta, I get sine alpha cosine beta, right? Plus cosine alpha sine beta. So any problem with this part? Look what I have. Okay, so I define A1 for A sine phi, A2 for A cosine phi, and we call this one. Phase. And this one will be because cosine phi, sine phi, they have pi over 2, right? Phase difference. We call this one in phase. We call this one phase quadrature. So let's see if I can, just 1 minute. If I can play by my A1 and A2, I can get whatever cosine phi you want, right? You want. So you don't have to play with phi over here, but you have A1 and A2 changed. Your phase for the signal is changed. It's changed. So let me. This is R. This is Q. This is phi. So for example, right? I use cosine, sine, so I can play with my A1 and A2, so I can have my different phases, Okay, so phi. So phi will be arctangent, right? Q over I, Q over I. So if you have a targeted phi in your mind, you can play with your Q and I, get this phi determined. Okay, no require, just know. I just want you know about it, right? So we can use IQ channel to play with different phases for your carrier signal. That's enough. Okay. Problem?
Yeah, I don't get how you got from X to T equaling that.
X of t equals, no, this is define, I define X of t is the sinusoid. Okay, any problem with that? No?
Yeah, how do you get that? Is that
Yeah, that is the equation.
property?
Yeah, no problem. This is the equation. New textbook. Let me see. No, this is not property. This is totally mathematics thing. So you have sine, right? You have sine A plus B. Yeah. So this is should be in your maths. I don't know, top one.
It's a trig, I believe, right?
Yeah. So in your maybe high school, right? Yeah, high school sine cosine. Okay. So now we talk about double sideband. We finished talking about double sideband suppressed carrier signal. Okay, here are some. Just a summary. This one, 100% efficiency. Bandwidth still, right? Twice as my original signal's bandwidth. Okay, every time your message passes 0, there will be phase reversal, phase change. Demodulation, way more complicated, right? Compared with your large carrier. So we have mixer, right? We have low pass filter, and for the mixer, we have phase lock loop and reference extraction. Okay, twice message rate. So still my bandwidth is twice compared with my original signal. So we achieve something, and we also want to input one more time. We want to improve the bandwidth. So we have the next member in this family called single sideband. Let's talk about the introduction stuff for single sideband and really the details for next lecture. Okay, right now, any problems, questions for suppressed carrier? So power is 100%, right? And the receiver is way more complicated. Okay, single sideband. This one we consider the best, right? The highest efficiency in power and also in bandwidth, single sideband. Okay, this is why, right? Why, and how can we do it? So double sideband, no matter it's large carrier or suppressed carrier, we have the twice of the bandwidth of my given signal. So we want to reduce the bandwidth to single sideband because each sideband carry all my information to recover it. Efficiency will be 100%. Okay, this time I improve my power efficiency, I improve my bandwidth efficiency, so make my transmitter and receiver, both of them are much more complicated. So we have to pay something, right, to get better performance. Okay, so let's look at why we mentioned single sideband can still do the work. So the first one is my original signal, right? Original signal. This one is double sideband suppressed carrier we mentioned before. If I have upper sideband only, okay, this one after mix, this one will go here, right? And over there. This one go here and over there. The high parts removed, so I can recover my original signal. If I have a lower sideband only, similar thing. So this one will go to this side. I still can cover my original information, so we can get the conclusion. Both upper sideband only or lower sideband only, we carry all the information we require to cover my information. So this is even single sideband can do the job, right? So any problem, how can I get this one? Now we talk about the difficulty, right, in my transmitter side and receiver side. So the straightforward way for, oh. We're going to talk about two methods to generate single sideband signal. The straightforward way, right? Generate double sideband and remove one sideband, so we get single sideband. The difficulty, the hard thing is this special filter. Let's look at one example. Okay, so we have a double sideband. I have a original message. This is double sideband suppressed carrier. Okay, we have a special design sideband filter. So this one we use it where we get the higher frequency, we get the upper sideband removed. Oh, I'm sorry. This one will pass rather upper sideband. So we have single sideband. Double sideband goes through filter, we get single sideband. So this is straightforward way. However, difficulty will be this filter. Okay, something outside this class. We talk about ideal low-pass filter, right? However, theoretically there is an ideal low-pass filter, but in real time, in real application, there is no such ideal low-pass filter. Okay, so this is my low-pass filter, right? Any frequency less than cutoff frequency can pass. Any frequency higher than omega c should be removed. Right, the gain is 1. We call it ideal low-pass filter. However, in real application, there is no such thing. So you may hear about different filters, right? In analog circuits like Butterworth filter, right? Sheffield filter, elliptic filter. So different filters. However, there is no something like this. Okay, the simplest one maybe Butterworth, right? Butterworth. Actually, in chapter 4, right, we show one second order Butterworth low-pass filter as example. So if this is ideal one, Butterworth filter will look like so for example, this is a second order Butterworth filter, right? And this is, for example, 10th order, right? 10th order, and the order higher, the circuit is more complicated. Your filter will closer to this ideal, right? Dashed shape. So this is Butterworth filter. We have pretty flat response in the pass band and the lower band. But still there is a transit from pass to block. So this is Butterworth filter. You may learn right from your filter design class, right, or some other classes. So this is real filter we can use in the circuits. Something like this. But the ideal rectangular one is mission impossible. If you really want smaller transit area, but you don't care about the flat response in the pass or stop band, we have some other choices. For example, yeah, I'm not sure about my my spelling. So chip filter is something like this. And let's see. So I have straight. So I have pretty good, right? So I have pretty good flat response here. And since I have oscillation, so I can get smaller, narrow transit area for chip tube filters. However, right, in your stop band, you have some ripples. And another cases for chip tube filter will be some ripples here, right, in the pass band, but pretty flat in the stop band. So those are the real filters you can use in your circuits. So there is no ideal one. So if we have upper band, lower band very close to each other, you don't have a good filter to remove one and keep another one. So why they say sideband filter is difficult if your two sideband are very close with each other, because the ideal sideband filter is also very hard or even impossible.